Welcome to the central force problem. Today we are going to discuss scattering in a central force field. Scattering phenomena are described in the same way, whether the underlying mechanics is classical or quantum in nature. Formulated as a one-body problem, the theory is concerned with the scattering of particles by a center of force. A uniform beam of particles is considered, all constituent particles having identical properties, and being incident upon the center of a force assumed to fall off to zero at very large distances. The intensity or flux density I represents the number of particles crossing unit area normal to the beam in unit time. The cross-section for scattering in a given direction is given by the following product. Sigma of direction omega is the differential scattering cross-section, and the omega is a differential of the solid angle, and their product is equal with the ratio between the number of particles scattered into the solid angle d omega per unit time and the incident intensity. Due to the fact that we are dealing with central forces, the problem has azimuthal symmetry around the incident direction of the beam, and as such the differential for the solid angle is given by the expression here. So it's 2 pi, which follows from the integration over the azimuthal angle times the differential of the scattering angle capital theta. The impact parameter S, which essentially measures the width of the beam relative to one of the incident particles, is by definition given by the expression here in terms of either in terms of the magnitude of the orbital angular momentum or of the total energy. So knowing the energy and the impact parameter will uniquely specify the scattering angle, which is the first major difference between classical and quantum scattering. If we assume that the impact parameter and the scattering angle are in a one-to-one correspondence, that is, we assume that to each scattering angle there corresponds to each impact parameter corresponds a unique scattering angle, and I cannot have multiple scattering angles for a given impact parameter, then the number of particles found within a differential element of the impact parameter ds has to be equal with the number of particles scattered in a differential angle capital theta. So the equality here holds automatically. And then since the impact parameter follows as a function of the scattering angle and the total energy, the expressions here can be inverted in order to obtain the differential cross-section as a function of the scattering angle as given by the expression here. For a purely repulsive scattering, the orbit is symmetric around the periapsis, and the scattering angle is given by the difference between pi and twice the angle denoted by capital psi, with capital psi being the angle between the incoming asymptote and the direction of the periapsis. And this follows very simply from a basic diagram of the scattering process. Then, if we go back to equation 336, and we use the following two conditions, namely that we choose the radius of the incoming particle to be infinite when for theta 0 equals pi, so we define this as the incoming direction of the beam, and we also want the periapsis to be found for to be located at the polar angle theta equals with pi minus psi. Then putting these together, we obtain the angle psi as the integral from the periapsis to infinity of this expression. And now if we use equation 390 for the impact parameter, together with this formula and the result here, we obtain the scattering angle as a function of the impact parameter according to the expression here. So involving this integral over the radial coordinate and the potential function. Furthermore, this result can be put in a different form if we change to the inverse of the radial variable for the transformation here, and we obtain this form. And these two expressions are normally used only for direct numerical integration of the scattering angle, though in some specific situations analytical results can also be obtained. Furthermore, from the result 396, we can use the transformation suggested here to find yet two other forms of the um, scattering angle as a function of the impact parameter, namely the two boxed results here. And these are quite convenient for numerical integration schemes. Furthermore, in the case of the latter expression, um, if we restrict the potentials to power law functions that are repulsive in nature, then you can see immediately that in the limit, when the radius vector tends to its periapsis value, the integrand behaves as the expression shown here. So it is therefore never singular. Now, using the expression 397 with the transformation given here and the conservation of energy written in this form, so the energy written as per its expression at the point of periapsis, where there is no radial velocity, then the scattering the scattering angle can be cast in this integral form. And this can be analyzed further in the limit of high energy scattering. So for high energies and low scattering angles, the condition being that the energy is much greater than the value of the potential at the periapsis, then essentially what happens is that the bracket here is approximately equal to 1, and then I can treat the entire quantity here, x, as a small number and use it in a Taylor expansion of the integrand, and this leads immediately to the expression here, which now contains two integrals. The first one can be solved immediately and is equal just to pi over 2, and so with that the scattering angle as a function of the impact parameter is approximately given by this result in the high energy limit. Furthermore, if we assume that the potential is a power law function, then we can work things out further to reach this expression. Now, this integral can, in principle, be evaluated using hypergeometric functions, but it is not necessary in order to reach an important physical conclusion. What is important is that if we go back to the expression of the energy, we can solve it for the impact parameter in order to write it in this way, and we can once again use the fact that we are assuming that we are working in the high energy limit. So then we can do a Taylor expansion of the square root to find the approximate value of the impact parameter as given here, and then once again we can use the formula connecting the potential and the scattering angle in order to write the impact parameter in this way. Now, from this same expression, we can actually go ahead and solve it for the inverse of the periapsis in order to find this relation of the inverse to the scattering angle. And at this point, we have found two important results. First, that in this approximation, the impact parameter is proportional to the periapsis. And secondly, that the inverse of the periapsis is proportional to the scattering angle at the power 1 over n, where n is the coefficient entering the power law of the potential. So the conclusion here straight away is that the derivative of the impact parameter with respect to the scattering angle is in absolute value proportional to this power of the scattering angle, and as such, the differential cross-section itself is proportional to 1 over the scattering angle at the power given here. So this is a very general result that is valid for high energy scattering in any repulsive power law potential. By analogy with our previous discussion regarding the Kepler problem, we can treat scattering in a attractive Coulomb field. So the force is going to be attractive in nature and given by the magnitude here, and so the force constant is just the quantity here, which would be this would be the product between the charges of two bodies, 2-point bodies interacting through an attractive Coulomb force. And we assume that the total energy is positive, so that they do not form a bound state, and then the eccentricities given by the formula we deduced previously, just with the replacement here. So it's this expression, and if we also use the formula 390 for the impact parameter, then the eccentricity can be written in terms of the energy and impact parameter as shown here. Then if we go back to the equation 355 for the integration constant theta prime equal with 0, then we obtain the angle of the periapsis or perihelion being equal with 0, and what follows immediately is the orbit equation for this new force constant. And now if we set the radius to infinity, so as the so this would correspond to the initial condition when the particle in the beam is infinitely far away, then the orbit equation will return for this radius. It will return the corresponding angle psi as having a cosine given by the expression here. So it's just minus 1 over the eccentricity. And if we go back to formula 394, connecting the angle psi to the scattering angle capital theta, then we can write this expression down for the scattering angle in two equivalent forms, either as a sine or the squared cotangent. And then if we use the formula we have deduced for the eccentricity, we can write down the cotangent of the scattering angle divided by 2 as being equal with the quantity here. So we can solve this expression for the scattering angle, for the impact parameter, and then using the definition of the differential cross section sigma, we we find the result given here. And you see that this is consistent with the general statement formulated earlier, because in the case of large energies, then the scattering angle is going to be small, so the cosecant here is going to be uh, approximately equal with uh, 1 over the scattering angle to the fourth power, and this is consistent with the general expression found previously, since uh, the power n is equal with 1 in the case of a Coulomb potential. Now, realistically, we deal in most situations with repulsive Coulomb scattering. So the first constant is given by the negative quantity here, and then we need to choose the integration constant for the polar variable as being equal with pi in order for the periapsis to be located at theta equals 0. Then the new orbit equation is given by the result here. So up to a change in sign, it is identical to the previous result, and uh, then the cosine of psi is equal with 1 over e. So the same relation is found between the scattering angle and eccentricity up to the sign. And obviously, both the impact parameter and the differential cross-section will functionally be identical with respect to the scattering angle. And this is the same result as in non-relativistic quantum mechanics. The reason being that the cross-section is a statistical quantity. It is not related to the trajectory of a given particle, but rather to the probability that a particle will be scattered in an angle theta, and so this result is the same whether the underlying mechanics is classical or quantum in nature. And as an illustration, this is this is a representation of the calculated differential cross-section for repulsive Coulomb scattering measured in barns as a function of the scattering angle measured in units of pi. And this is the result observed in the classical Rutherford experiment from the early 20th century. So that there is a large cross section at small angles, meaning that most particles in the beam fly undeflected. In his case, the beam was made from a source of alpha particles scattered on a thin gold foil. So most particles would pass through the foil deflected at very small angles, but uh, he would also observe a small number of particles scattered at very large angles. So there was a non-vanishing amount of backscattering, and this led to the hypothesis that the uh, atom is made mostly of empty space and having the positive charge concentrated in a very small volume at its core, which came to be known as the atomic nucleus. Another example where the scattering angle can be calculated analytically for integration is that of an inverse cubic repulsive force. So a force given by this expression, for which the potential is given here, and then the scattering angle as a function of the impact parameter follows as pi minus 2 times this integral. And then for one thing, we solve the conservation of energy for the for the perihelion radius, and we use this change of variables in order to rewrite the result here in this simpler form, involving a much more manageable integral. And to go further, we make a new change of variables given by u equal with the sign of a variable v, which allows the straightforward integration in the result here. So this is the scattering angle as a function of the impact parameter. And then if we once again change variables by denoting the ratio of theta to pi with x, then we can solve this expression for the impact parameter and obtain the result here. Also, we can take the derivative of the scattering angle with respect to the impact parameter to obtain the formula here, and then bringing these in the definition of the cross section, we finally obtain this this boxed result. The total cross-section is defined as the integral of the differential cross-section over the full solid angle, so over 4 pi, which in the case of the central force problem simplifies to the product between 2 pi and the integral over the differential cross-section of the differential cross-section over the scattering angle from 0 to pi. And as an example of the evaluation of this quantity, we can consider the spherical well potential. So a potential that is equal to 0 for any radius r larger than some value a, and the constant value minus v0 for all radii which are less or equal with a. We will define the angle alpha as having the sinus given by the ratio between the impact parameter of the particle and the radius of the sphere. And we will note the following things. Inside of the spherical well, the magnitude of the velocity will be denoted by v1, and the dot product between the incident velocity and the normal to the surface of the sphere at that point is going to be equal with v1 times the cosine of an angle beta. Furthermore, we use the conservation of angular momentum as the value of L, given the spherical symmetry of the problem. The magnitude of L must be the same whether written in the external or internal variables. So putting these two together, we find the relationship between the angles alpha and beta being one of proportionality, with the proportionality constant n being simply the ratio between the velocity inside the spherical well and the incident velocity. And this formula is reminiscent of Snell's law from geometrical optics, and such that n can be interpreted as a refraction index. And since we have obtained its value as the ratio here, this can be written further, solved further using the conservation of energy. So the energy of the particle must be the same whether we are discussing the region outside or within the sphere. So putting these things together, it follows that the refraction index is given by the expression here. This quantity is greater than 1, and as such the angle beta is smaller than the angle alpha, and so the particle is effectively attracted inside the well. And if you draw a simple diagram, it is seen immediately that then the scattering angle is simply 2 times the difference of these two angles. Then we have defined the sinus of alpha as the ratio between the impact parameter and the radius of the sphere, and using this result we can write this ratio as given here, and we also have effectively the refraction law obtained earlier. So putting the two together, we can solve for the impact parameter to obtain it as a function of the scattering angle and the refraction index. And then we can also immediately calculate its derivative and the corresponding cross section. And knowing this, we can then calculate the total cross section by performing the integral directly. What is important to note here is that there exists a cutoff angle, theta m. This corresponds to the value of the impact parameter, which is equal with the radius of the sphere. If the impact parameter is greater than this value, then effectively no scattering takes place, as the particles can continue flying through space undeflected. And so for this particular value of s, we can calculate the the value of the cutoff angle from the formula here to obtain this result, and then putting this in the expression of the total cross section, we finally obtain the result here. And this is in fact different from the quantum mechanical result, due to the fact that in quantum mechanics there is there is an additional contribution from particles being reflected on the spherical well, so something which does not happen classically. And so as an illustration, the cross section here is represented, once again calculated in barns, is represented as a function of the scattering angle measured in units of pi, and has this behavior. So there is a very large transmission at small angles and at small scattering angles, and then the cross section steadily decreases until it reaches the cutoff value. If we were to perform the same calculation in the case of the Coulomb field, in order to obtain the total cross section, we would have to evaluate this integral, which is done in a simple manner through the change of variables here, but we discovered that it leads to a divergent result, namely an infinite total cross section. This is because the total cross section represents the total number of particles scattered in all directions per unit time for unit incident intensity. As the Coulomb field itself is long range and extends to infinity, all incident particles are scattered to some extent, leading to a divergent result. This remains true for any long-ranged classical field. In quantum mechanics, however, potentials falling off faster than 1 over r squared have finite total scattering cross-sections. This is due to the asymptotic behavior of the scattering solutions of the Schrödinger equation, which for such potentials are a linear superposition of plane and spherical waves. For finite classical results, the fields must be cut off past a certain distance, which in Rutherford scattering is possible, for example, through electron screening. To see how this would work, consider the screened Coulomb potential given by the expressions here. So it's a Coulomb field minus a constant given by the ratio of the force constant K and a radius A, which has the significance of the effective radius of the atom. And as such, this expression is true for all radii less or equal to A, and the potential is considered zero for radii larger than A. So the field of the nucleus is screened by the electron cloud beyond the effective atomic radius A. And then the scattering angle would have to be calculated in two instances. One, when the impact parameter is small enough that the projectile can penetrate inside the electron cloud and interact with the nucleus. And the second instance, when the impact parameter is so large that the projectile never intersects the atom. Then in the first case, we write down the expression of the scattering angle as a function of the impact parameter given by the radial integral here. And we simply break the integral down into two parts, one going from periapsis to the atomic radius, and one from the atomic radius to infinity. And the first integral is written in terms of an additional constant kappa, which is given by the sum here. Now, it is straightforward to carry out these integrals, and the result in the first case is the expression here, which involves a couple of new additional parameters, namely an eccentricity E given by this expression, or equivalently the one here, and both this one and the formula above also involve the parameter x, which is just the ratio between the impact parameter and the atomic radius. And naturally, in the second case, the scattering angle as a function of the impact parameter is always going to be zero, as the particles will be flying undeflected by the atom. In any case, returning to the first result, even though it looks complicated, it is in fact quite easy to evaluate. So from this expression, the sinus of theta 1 divided by 2 can be written immediately in as this ratio, and from this we can solve for the impact parameter in order to find this dependence on the scattering angle. And then using the definition of the differential cross section, we can rewrite it first of all in the equivalent form here, which is obviously it gives the same result as the expression here, and when put in this form, it allows for a simpler evaluation and leads to the boxed result here. And then in order to calculate the total cross section, we simply integrate the differential result from 0 to pi in order to obtain finally the result here. So in terms of the total cross section, a screened Coulomb potential effectively behaves like a spherical well of finite radius. As another example of a screened Coulomb potential, we can now consider the classical repulsive scattering by an atomic nucleus of finite radius A. So in this case, the potential is going to be approximated with a constant value, the force constant divided by the radius of the nucleus, for radii smaller than this particular value, and the usual repulsive Coulomb field for larger radii. And we are going to study specifically the case where the total energy is greater than the constant here. once again, we need to consider two situations. The first one is the one where the impact parameter is small enough that the particle undergoes Coulomb scattering initially, then gets inside the nucleus where the potential is constant. It travels through this constant potential, and it scatters in a Coulomb field once again upon leaving the nucleus. And the second case is the one which the impact parameter is so large that the particle never manages to penetrate the nucleus anymore, and the whole dynamics is described by the usual Rutherford scattering. So in the first case, we write the scattering angle down as a function of the impact parameter. And it's the as given by the familiar integral here. And once again, we break this into two parts. A sum of two integrals, one involving integration from the periapsis to the nuclear radius, and the second term involving the integration from the nuclear radius to infinity, with the potential written accordingly in both regimes. And we need to now to consider a few things. The periapsis radius is simply given by the radius of the nucleus times the sinus of the angle alpha, which is which is seen just by drawing a small diagram. So for the first situation where the particle manages to get inside the nucleus, we can parameterize this ratio using the angle here, and then we can once again use the conservation of angular momentum. First of all, to write the angular momentum in the coordinates corresponding to the particle being on the surface of the nucleus, as seen in these internal coordinates. So for motion inside the nucleus, these are the velocity at that point and the sinus of alpha. And we can also write the same value of the orbital angular momentum using the total energy and the initial impact parameter. And if we were to put these things together, we can add one additional condition. Namely, we can imagine writing down the total energy for the specific case in which the impact parameter S0 is chosen in such a way that the periapsis corresponds to the radius of the nucleus. So putting these things together, we can find the radius of the periapsis in terms of the impact parameter and the total energy. And then if we were to also use this condition, then we can express the periapsis simply as the product between the nuclear radius A and the parameter x, which is just the ratio of S to S0. So it's an arbitrary impact parameter divided by that impact parameter, which would result in the periapsis being equal of the nuclear radius. And then the integration is straightforward, and it leads to the general result here for the scattering angle in terms of the parameter x and the eccentricity E having the expression here. Now in the second situation where the periapsis lies beyond the nuclear radius, we simply discuss about the conventional Rutherford scattering or Coulomb scattering, and then the scattering angle has the familiar expression, which is equivalent to the result here, and this one is found by carrying out the integral directly, as opposed to the method we used previously. So these would be the formulas of the scattering angles in both situations in terms of this parameter x. Now, In the particular case where the energy would have the value here, the corresponding scattering angles would be given uh, by these formulas as functions of the impact parameter, and they are illustrated in the following figure. So this is the scattering angle measured in units of pi as a function of the ratio x. So this is the impact parameter divided by the value of the impact parameter, which would result in the periapsis lying on the nuclear radius for the specific value of the energy given here. And the result is the one represented in the continuous line. So at when this parameter is 0, we have that the scattering angle is also equal to 0, so the particles are simply transmitted through the nucleus. And then as this parameter increases, so does the scattering angle up until we reach the surface of the nucleus. And from that point on, for larger values of this parameter, um, the scattering angle decreases, and it decreases on the trend that would follow from usual Rutherford scattering, which is represented by the dotted line. Another important point to be made on this figure uh, is that there is a discontinuity in the scattering angle as a function of x when x is equal to 1. So for an impact parameter which would correspond to the periapsis being located on the nuclear surface, namely when evaluating uh, the limit from the left side, the derivative here is infinite. So since this is infinite, the inverse is 0, and the implication is that the cross section itself is 0 for so there is no scattering possible in a direction that is tangent to the surface of the sphere. And this is a bit different from what we are going to discuss in the following. Um, Namely, we begin from the observation that in Rutherford scattering, or in conventional Coulomb scattering, the scattering angle is a smooth monotonic function of the impact parameter. So the implication of equation 3.101 is that when the impact parameter goes to infinity, the scattering angle goes to 0, and when the impact parameter goes to 0, the scattering angle goes to pi. However, this is not always the case, and equation 393, which is the differential cross-section, is not always valid. As an example, one can have a situation where the scattering angle goes to 0 both for infinitely large and for a vanishing impact parameter, and then the function has a maximum value that m in between. For scattering angles smaller than this maximum value, two values of the impact parameter result in the same scattering angle, and hence the equation 393 has to be replaced by a differential cross-section given by a sum of such expressions, where the index I takes two values for angles that are different from the maximal scattering value. However, at the maximal value of the scattering angle, the derivative of the scattering angle with respect to the impact parameter vanishes, and as such the differential cross-section in this limit becomes infinite, while for values that are larger, for scattering angles larger than the maximal value, the cross-section, the differential cross-section vanishes. And this is known as rainbow scattering, which is a name given in analogy of geometrical optics and the scattering of light rays from water droplets. To illustrate this, we can once again consider the scattering of a particle on a nucleus, which itself will be considered point-like for this example. So the potential is a Coulomb-like potential, which for vanishing radius will reduce to a constant value, a constant finite value concentrated at the origin. And we will be interested in the particular situation where the energy is equal with this value. It's 1.2 times V0 divided by R0. For simplicity, we will take this parameter to be equal to 1. And then we use the integral of equation 397 to calculate the scattering angle as a function of the impact parameter using this change of variables. So with these things put together, the scattering angle is given by the expression here. We state the conservation of energy using its value at the point of at periapsis, and we equate this with the fact that we have chosen this particular value for the energy of the beam. And putting the two together, we obtain a cubic equation for the periapsis parameterized by the impact parameter. And this equation can be solved through the bisection method, while the scattering integral itself can be solved through the Gauss-Chebyshev quadrature. And I've linked an article where this is discussed in detail. Here I will only give the main results, namely the Gauss-Chebyshev quadrature is a numerical method used to evaluate integrals of this kind. And it states that such integrals are which you can see. So it's an integral of the type here, and it is equal with this sum, where the weights W are all taken in this case are taken to be equal. They are given by the ratio of pi to capital N, and the variables y of index I are just the roots of the Chebyshev polynomials of order I, having these expressions, and n is taken here to be equal with 800. So it is very straightforward to perform this evaluation, and I've represented some of the results as a series of figures. This would be the potential as a function of radius in unspecified units, and we are studying the case where the energy, the total energy, is has the value here. Okay, all right. This is the these are the values of the cubic form here as a function of x for two given sets of impact parameters. So this would be the evolution of the expression when s is 0, when this is the its evolution when s is equal with 10, and there is a root here. So in any case, this is found for the bisection method. I just wanted to illustrate where the roots are likely to be found for some reasonable value of the impact parameter. And then the scattering angle as a function of the impact parameter has a has the following dependence. It rises sharply from from a vanishing value when s goes to 0, and but it plateaus fairly quickly at a small impact parameter, and then it continues to decrease for larger values. And the differential cross section as a function of the scattering angle then has the behavior represented here. The peak seen at this value corresponds to the maximum of the scattering angle, and obviously for larger values of the angle, the cross section vanishes since there is no scattering at those values of the angles. But uh, for uh, for smaller values, that there are actually two branches. There is a very small branch of the cross section, and there's another one which increases quite rapidly as the scattering angle vanishes. In the case of attractive potentials, it is possible for the angle psi to be greater than pi over 2, which would imply that the scattering angle itself is negative. This is not necessarily problematic, as only magnitudes are involved in the calculation of the differential cross-section. However, on the basis of equation 396, it becomes possible for the scattering angle to be larger than 2 pi. Which effectively implies that the particle orbits the center of force for one or more revolutions before being scattered. As an example of this phenomenon, one can consider the so-called Lennard-Jones 612 potential, given by the expression here. Historically, this potential was treated in a famous article by Joseph Hirschfelder, written in 1948. Hirschfelder also wrote a famous treatise on molecular dynamics and classical and quantum transport theories. But the calculation methods used then, at least for numerical computation, are a bit dated at present, since we have modern computers and modern methods, and it is a lot easier to study this potential numerically using the Gauss-Chebyshev quadrature introduced previously. So in any case, we will study this potential with the parametrization here, which is the standard parametrization found in the literature for hydrogen molecules. So you see this potential has two parts: a repulsive core and an attractive component that is of a longer range. And as a qualitative discussion, the effective potential in milli-electron volts, so the Lennard-Jones plus centrifugal barrier, is represented in this figure as a function of the radius measured in angstroms, and for different values of the impact parameter. So what we see is that when the S0 corresponds to a nearly vanishing impact parameter, so there is virtually no centrifugal barrier, and the effective potential looks fairly similar to situations we have previously discussed. There's a repulsive core at short ranges, which is now intrinsic in the structure of the potential itself, and there is the attractive part at the larger radii, and then as the impact parameter increases and the centrifugal barrier is added to this to the bare potential, we notice the development of a small hump. So this hump develops over range of impact parameters up until some critical value where it flattens out, and from that point on it vanishes completely, leading to a purely repulsive potential dominated by the centrifugal barrier. Now, for configurations in energy and impact parameter leading to a hump in the potential, the radial velocity is nearly vanishing in the proximity of the hump, while the angular velocity remains unaffected, as is seen from the uh, conservation of angular momentum. Therefore, in the time it takes for the particle to traverse the radial region of the hump, it may undergo one or more revolutions. This phenomenon is known as orbiting or spiraling. Past the critical values where the well and hump flatten out, orbiting no longer occurs, but zero deflection is still possible due to the combined effects of the attraction and repulsion. For high energies and low impact parameters, the short-range repulsive potential dominates, leading to a dynamics qualitatively similar to Rutherford scattering. The deflection angle phi is given by the right-hand side of equations 396 or 397, such that the scattering angle is plus minus the deflection angle minus 2 times m times pi, where m is a natural number chosen such that the scattering angle itself lies between 0 and pi. So essentially m will count the number of revolutions. And as an illustration, these are the results obtained in evaluating the scattering integral. So for the deflection angle measured in units of pi as a function of the impact parameter measured in angstroms, for the Lennard-Jones potential parameterized for hydrogen molecules using these two particular values of the energy. So the continuous line corresponds to the energy here, and we observe that at a vanishing impact parameter, we have a situation of backscattering. So the particles would be completely repelled by the field. Then, as the impact parameter begins to increase, the deflection angle decreases. At some value, it crosses zero. So this is the point where the particles in the beam fly undeflected for the field, and then the deflection angle continues to decrease. So the particles are deviated in the opposite direction up to some minimal value, after which they once again the deflection angle starts to approach zero. So particles once again fly undeflected. The dashed line corresponds to a smaller value of the energy, and the behavior is qualitatively quite similar, except for the fact that we no longer find a minimum in the deflection angle, but rather there is a value of the impact parameter for which the deflection angle is singular. So as we approach this value of the impact parameter, the deflection angle in magnitude goes towards infinity. So in other words, the particles are undergoing more and more revolutions or spirals in this potential before managing to escape. To list a few more important facts regarding classical scattering theory, first of all, we note that when the scattering angle goes to zero for a finite value of the impact parameter, the differential cross-section becomes infinite in the forward direction. So this can also occur in the backward direction, provided that this quantity remains finite when the scattering angle goes to pi. And this is known as Glory scattering in analogy to a phenomenon known in meteorological optics. Furthermore, the scattering of low energy ions on a crystal lattice is a quantum phenomenon with a classical solution. Even in the case of stronger quantum effects, semi-classical approximations involving knowledge of the classical trajectory often remain useful. In almost all practical situations, equation 3.96 or equivalent formulations must either be approximated by analytic functions in a certain range of impact parameters or integrated numerically. And we have, throughout this discussion, we have seen examples of both situations. Also, it is relevant to note that general analytic forms of the orbit often do not exist. In summary, we have defined the fundamental quantities relevant for scattering and central force fields, namely the impact parameter, the scattering angle, the differential and total cross-section, and we have determined the relations between them. We have studied scattering in attractive and repulsive potentials, with particular emphasis on the spherical well, Coulomb scattering, and molecular potentials. We discussed exotic phenomena such as rainbow scattering, glory scattering, and orbiting. In the following, we will discuss the transformation of the scattering problem to laboratory coordinates. All that being said, I want to thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.